Hello, welcome to PhyzQuest. So this is the solution video for CSIR NET December 2019 Part C, question number 4. So question is the Bethe-Weizsacker's formula for the binding energy in megaelectron volt of a nucleus of atomic number Z and mass number A is given. We need to find out the ratio Z by A for the most stable isobar of A equal to 64 nucleus. So 4 options are given and we need to choose the correct option. So let's get started. So this question comes from the section Nuclear and Particle Physics, and the concept involved here is semi-empirical mass formula. So here we are given a formula to calculate the binding energy of the nucleus, which is known as Bethe-Weizsacker's formula, also known as the semi-empirical mass formula, which has a collection of different terms. Now when we talk about the nuclear binding energy, nucleus is formed by combining the nucleons. By combining here means they form a bound system, so that certain amount of energy, see here bound system means therefore a strong force holds them together, so that a certain amount of energy is needed to separate them. That energy is known as the binding energy. Now when we talk about bound system has lesser mass than its separate constituents. Therefore, the mass of the nucleus is smaller than the sum of the masses of its constituent nucleons. Now, this difference in mass creates a mass defect. So, this mass defect actually represents the mass of the energy which is binding the nucleus. So, the mass defect, when converted to energy by using the energy formula E equal to delta mc square, where delta m is the mass defect, it provides the binding energy. So this Bethe-Weizsacker's formula provided the refined expression of the binding energy, which is composed of a certain number of terms expressed in terms of mass number A and atomic number Z, along with some coefficients. Now, one of the application of this formula is to find out the most stable isobar for a given mass number A. Now, the definition of isobar is same atomic number but different, same atomic mass but different atomic number. Now, most stable isobar means the one with maximum binding energy. Therefore, it is very much difficult to separate it into its separate constituents. So, now to find out the most, our question is to find out the ratio of Z by A for the most stable isobar. And now first of all, we have to find out what is the most stable isobar for a given A. So we need to find out the value of Z for which the binding energy is maximum. Because as I said, for maximum binding energy, it will be the most stable one. So to find that out, we need to differentiate the binding energy with respect to Z, keeping A constant. And the point of maxima of the first derivative should go to 0. So that therefore del P by del Z when A constant should be equal to 0. This is the condition to find out the most stable isobar. So here this is the expression we are given for the binding energy. So when we differentiate it with respect to Z, keeping A constant, first two terms will be 0 because we are keeping already A as constant. Now we have to differentiate these two terms. So when we differentiate that, it will give you minus 0.714 2Z minus 1 divided by A to the power 1 by 3 minus 23.2 into 2 into A minus 2Z into minus 2 divided by A. So this will be equal to 0. Now upon calculating this, A is taken as constant, we have to find out the expression of Z from this. So ultimately upon final calculation, Z will be calculated as A plus 0.008 A to the power 2 by 3 divided by 1.98 plus 0.016 a to the power 2 by 3. In our question, it is given as a, we have to find out the stable isobar when a is equal to 64. So in this given expression, we will put a as 64. So this will be 64 plus 0.008, 64 to the power 2 by 3 divided by 1.98 plus 0.016, 64 to the power 2 by 3. So upon final calculation, this will be comes out as equal to 28.679. So we have to find out the ratio of Z by A for most stable isobar. This is the value of Z for most stable isobar. And we have A already given as 64. So Z by A will be equal to 28.679 by 64, which is equal to 0.45. Now let's check the option. So if you check the option here, you can see that option C is matching with our result. So the correct answer for this question is option C.